we will continue our discussion on principle of hydraulic machine and system design. Today we will solve the problem that we have discussed in the last lecture. So, the problem is on slip. I mean, as we have discussed that because of the slip, the actual head developed by the pump deviates from that predicted by the Euler equation. So, the problem statement is a 8 bladed radial flow pump has an impeller exit diameter of 20 centimeter. The width of the flow passes at the impeller outlet being 1.5 centimeter. The backward curved vanes make an angle 60 degree with the axial direction. There is a mistake in the problem statement. The backward curved vane makes an angle, it will be the backward curved vane. I am writing the backward curved vane, make an angle of 30 degree with the axial direction. So, there is a mistake. So, this would be 30 degree, that backward curved vane make an angle 30 degree with the axial direction. The pump runs at 2880 rpm. We need to show that the head developed by the pump is related to the flow rate. H is equal to 74.4 minus 565.1 cube. We need to ignore the blockage effect and all losses, and finally we need to sketch the relationship, and again we need to make a comment on that relationship and how we can expect that the actual head flow characteristic will look like. Okay, so now we will proceed to solve the problem. So, we will solve the problem. So, this is a radial flow pump. So, we need to draw an impeller, schematic of the impeller of a radial flow pump. So, initially we should draw the impeller of a radial flow pump which is having backward curved vanes. So, these are the backward curved vanes. So, impeller is rotating in the clockwise direction at an angular velocity omega, right, this in the clockwise direction, and we need to draw the velocity triangles at the outlet of the impeller. So, if I identify a particular blade by inlet is 1, outlet is at 2, then if I draw this, if I take out this blade and if I draw the velocity triangles at the outlet, and we can obtain velocity components So, this is beta 2 blade angle, this is u2, and this component is absolute velocity c2. So, this is 0.2 at the outlet. It is given that backward curved vanes make an angle 30 degree with the axial direction. So, this is beta 2, this beta 2 is 30 degree given. Pump runs at 2880 rpm, that is also given. D2 exit diameter is given 20 centimeter and width is given B2 is 1.5 centimeter. So, if I draw the impeller again, and this is the width. So, this width is given B2, that is 1.5 centimeter. So, width of the impeller is given, outlet diameter D2 is given, and we have drawn the velocity triangle, this is W2, but an important point that we need to take into account is that it is written that outlet flow direction follows the blade angle closely in absence of rotation. That means, whenever pump is not rotating, in absence of rotation, the outlet flow angle follows the blade angle, but whenever pump will start rotating, the outlet flow angle will deviate. That means, there is a presence of slip. So, this sentence is an indication of that we need to take the effect of slip into account while you are solving the problem. So, here we need to take this effect of slip. So, in presence of slip we have seen that if I can recall that the resultant force will shift the absolute velocity and relative velocity to their new position. So, if I draw this is the changed absolute velocity c2 prime, and similarly this is the w2 prime. So, this will be beta 2 dash. So, as we have discussed that the angle changes from beta 2 to beta 2 prime because of this resultant force that is acting on the forward surface of the blade, and which is responsible for the deviation of actual head from the Euler head, from the head predicted by the Euler equation. So, now this is this is c theta 2 and this is component of absolute velocity while we are considering the slip, and this is known as the slip velocity Vs. So, we have to solve this problem. Since no information is given about the effect of inlet swirl, we are assuming that no swirl at the inlet, no swirl at the inlet, that is c theta 1 is equal to 0. Now, we need to solve the problem. N is given, beta 2 is given, d2 is given and b2 is given. So, if I recall the Euler equation which will gives us an information about the head developed by the palm, that is H is equal to u2 c theta 2 minus u1 c theta 1 by g. Since we have assumed that rather no information is given about the effect of inlet swirl, we have assumed inlet swirl component is 0, there is no inlet swirl, there is purely radial inlet, that is purely radial inlet. That means head developed by the pump will be u2 c theta 2 by g. Now, since we are going to consider the effect of slip, probably the component of absolute velocity, that is all very important component for the head which is being developed by the pump, that is c theta 2 will be c theta 2 prime for the present case. So, now we will look at the effect, we look at the velocity tangles at the outlet. So, now what is the tangential velocity? Tangential velocity at the outlet u2 is equal to pi d2 n by 60, and pi d2 is given, diameter of the outlet is given 20 centimeter, n is given 2880 rpm, and if we calculate 0.2 meter twice 880 rpm divided by 60, we will get velocity is near about 30.15 meter per second. So, tangential velocity at the outlet is 30.15 meter per second. So, as I said that the Euler's equation for this case will be u2 c theta 2 by g. It is not correct, because if we consider slip, and that we need to take into account, because it is written that when pump is rotating, the blade angle does not, the flow direction does not, in presence of rotation, the flow angle, blade angle, the outlet flow direction, may not match, rather does not match with the blade angle. So, it is given that whenever no rotation is there, that is in absence of rotation, flow direction will match the blade angle, closely, but whenever pump will start rotating, there might be a deviation. So, we need to take the effect of slip into account from this information. Okay, if we consider the effect of slip into account, then we can write this expression that the component of absolute velocity in the tangential direction will be c theta 2 prime. So, that is the head that will be developed by the pump, which is given in the problem statement. So, now if we consider the velocity angle again, just again I am drawing the velocity angles here, this is U2 and this is C2, this is C2 prime, this is C theta 2 dash, this is Vs, and this will be actual C theta 2 component, and this angle beta 2 is given this is W2 prime. Now from the velocity angle itself I can write that C theta 2 prime will be equal to C theta 2 minus Vs, that is we can write. So I can replace the value of C theta 2, that is C theta 2 minus Vs divided by G, that we can obtain from this velocity triangle, that C theta 2 will be C theta 2 prime plus Vs, that means C theta 2 prime is equal to C theta 2 minus Vs, where Vs is equal to slip velocity, that we have obtained the expression of slip velocity in the last lecture, that is equal to pi u2 sin beta 2 divided by z, pi u2 sin beta 2 by z, and z is equal to number of blades is equal to 8, which is given for this problem. So the number of blades is 8 and slip velocity is calculated based on Stodola's slip model. This is essentially based on Stodola's model. So pi u2 sin beta 2 by z, u2 we have calculated already, we know beta 2. So if I put the value of Vs, then expression of H will be u2 C theta 2 minus pi u2 sin beta 2 by z divided by g. Now again from the velocity triangle, from this velocity triangle we can write that C theta 2 is equal to u2 minus w theta 2, because this is w theta 2. If we look at the expression of H that we have obtained for the present case, which is having C theta 2, so we need to know an information about C theta 2. In this expression we know everything except C theta 2, because we know beta 2, we know Z, we know the magnitude of tangential velocity at the blade outlet, but we do not know the magnitude of C theta 2. So we need to calculate C theta 2 from the velocity triangle. So I can write from the velocity triangle that C theta 2 is equal to u2 minus w theta 2. I know the value magnitude of u2. So u2 and w theta 2 is very important, that I can obtain from the expression, and here I will write that this component in the radial direction perpendicular, which is known as CR2, that is flow velocity. This CR2 is called flow velocity. So from the velocity triangle I can write w theta 2 that equal to CR2, this is w theta 2 and this will be CR2, shows w theta 2 by CR2 is equal to cot beta 2. So it would be this by this, that is CR2 by w theta 2 is equal to tan beta 2. So w theta 2, that is CR2 by w theta 2 from this triangle will be equal to tan beta 2. So w theta 2 is equal to CR2 by tan beta 2, that is CR2 cot beta 2. So we have obtained the expression of C theta 2 in terms of known quantities, but here again we are having another unknown quantity, that is CR2, that is flow velocity. So we need to know again what will be the magnitude of flow velocity, otherwise everything we know from this expression. So if we again, it is given that the d2 is equal to 20 centimeter, that is 0.2 meter, b2 is equal to given 1.5 centimeter, that is 0.15 meter, that is equal to given. Now we have to calculate CR2, very important, mind it, the problem statement is giving us, is asking to relate, to establish a relationship between H and Q. So, here we do not know an explicit magnitude of, we do not know the magnitude of Cr2, but I can relate Cr2 in terms of the flow rate. So, if I go back to my previous slides and if we see that here the flow area will be, this is the flow area. So, whenever liquid is coming out from the impeller, whenever fluid is flowing in the passage between two blades, so this is the flow area, hatched portion is the flow area, this is the flow area. So, flow area, that is Q, flow rate will be area, flow area into flow velocity, and this flow velocity is Cr2, that is, if flow velocity, that is Cr2, I am again mentioning here. So, flow velocity is Cr2, that is Cr2 will be Q divided by flow area. So, now if I go to the next slides, so I can write that Cr2, that is flow velocity is equal to Q divided by flow area, and the flow area from the figure itself will be, this flow area will be pi d2 into b2, that is diameter at the outlet, I know the width. So, pi into d2 into b2 is the flow area. So, I can calculate the Cr2 from this expression. So, if I write again the expression of H, that H is equal to U2 by G and U2 minus C theta 2, C theta 2 is equal to U2 minus Cr2 cot beta 2. So, if I write the expression of C2 over there, that is U2 minus Cr2 cot beta 2 minus pi U2 sin beta 2 by Z minus pi U2 sin beta 2 by Z. Here just I am putting the magnitude of Cr2, that is U2 by Z into U2 minus Q divided by pi d2 b2 cot beta 2 minus pi U2 sin beta 2 by Z. So, this is the H expression of H which can be related in terms of Q, and if I calculate this expression, I know the magnitude of U2 that we have calculated is coming around 30 0.15 meter per second, beta 2 is given 30 degree, d2 and b2 are given. So, if I calculate the magnitude of this quantity, I will obtain the expression that H is equal to 30.15 divided by 9.81 into 30.15 minus cube into cot 30 degree divided by pi, that is into 0.2 into 0.015, sorry, this is 0.015, this is 0.0, this is 0.015 meter, 0.15 minus pi into 30.15 sin 30 divided by 8. So, if we calculate this, we will get the final expression is 74.47 minus 565.1 cube. So, this is what we need to establish, that the head can be related in with the discharge following this relationship. That means, if you take the effect of slip into account, actual head developed by the pump may not be equal to the head predicted by the Euler equation. So, here although we are following the Euler equation, but we are considering the effect of slip, and we have calculated the magnitude of slip following the Stradula's model, and we got the expression of that 70 H can be related in terms of 74.47 minus 560.1 cube. Now, last part is that if I draw, so from this H cube curve I can draw the H cube characteristics. So, if I go back to the my previous slide, now if I make Q is equal to 0, I will get the magnitude of H, that is 74.47. So, when q is equal to 0, so this is 74.47 when q is equal to 0. So, this is the q, this is h. So, this is h, and whenever I make h is equal to 0, then I can get q is equal to, it will cut over here, and this point q will be equal to 74.47 divided by 560. So, this will be 74.47 divided by 565.1. So, this is the actual HQ curve, I mean following the relationship that we have obtained, but I would expect a different curve from that what we can obtain from the HQ relationship, because as I said you, although we have taken into account the effect of slip, but there will be a recirculation losses in the suction side that we have discussed, that because of non-uniform velocities, because whenever liquid is flowing through the pipe, boundary layer will start forming and velocity may not be uniform all along the pipe, I mean in a given cross section. So, velocity will change from one point to other point in a given cross section. So, because of this non-uniformity in the velocity distribution, there will be a recirculation loss in the pipe suction, suction side, as a result of which this head I may not get, and the actual curve will be like this. Actual curve will be like this. So, here we will have some losses, and also here we will have some losses at the delivery side. So, this is losses in the suction side because of recirculation losses, and here we also have some losses, that is frictional losses at the or separational losses at the delivery side. So, the actual curve that I would like to expect is, the actual curve look like this, but if we draw the H cube curve following the relationship that we have established, that will be a straight line, but the actual curve will be look like this. So, this will be the actual curve, because we need to take the effect of recirculation losses, also the frictional losses, recirculation losses in the suction side and the frictional losses in the delivery side into account. So, this is all about the problem that we have solved. So, maybe if we normally a centrifugal pump testing we will discuss, where we vary the flow rate and we calculate the H that is developed by the pump, and from there if we tabulate the H cube data, we can obtain the H cube curve, and H cube curve should be a straight line from whatever we have obtained from this problem also. But in actual case it should not be like this, but sort of head should be reduced. So, because of the recirculation losses at the suction side, also there will be some losses at the pump delivery side. So, the actual curve will not be a straight line. Okay. With this I will proceed to the next part, but I would like to discuss another important point in this lecture, that when we have derived the expression of slip velocity following Stradula's model, and we have Stradula assumed that if a velocity can be inscribed, if a circle can be inscribed at the outlet of the impeller is having radius E, then probably slip velocity is the product of omega, that is the angular velocity at which impeller is rotating, into E. So, rather the product of relative AD into E, where if, as I said, that if impeller is rotating at an angular velocity omega, then the fluid must have a rotation related to the impeller is minus negative omega. So, this omega product E is the slip velocity. So, we have tried to calculate, we have tried to obtain a new a numerical expression of the slip velocity using a Stradula's model, and if we go back, we have seen that this is the circle. So, here this is the portion of the length along the periphery between two blades, a portion of the length along the periphery of the impeller between two blades, which is nothing but 2 pi r2 by z, and we are approximating this length will be equal to the sides of this triangle, that is, if I give a name E F G, then the side F G, we are approximating the side of this length, the magnitude of this length, that is G F, is almost equal to the length of the periphery of the impeller between two adjacent blades, that is twice pi r2 by z. So, a portion which is length of the portion between two adjacent blades is 2 pi r2 by z, that is equal to the length GF in a triangle EGF that we are approximating, and that is the approximation we have done in the Stradula's model to obtain the numerical value of slip velocity. And this is true because the blade angle for a given blade angle, and probably we have assumed that the circle, the maximum, the largest circle which can be inscribed between the at the outlet of the impeller, if E, then probably this approximation is not very bad approximation. So, with this we will proceed to the next part of this course.